Good morning, everyone. My name is Haenan from Gaia 3D, and this is my first presentation at Global FOSS4G, and this might be boring. So thanks in advance for your patience. Today, I am here to talk about AI-powered wildfire spread prediction system using open-source geospatial technologies. In my presentation, I'll explain why we developed this technology, how we develop it, and share our progress. Finally, I'll show you our system. First, let me explain the background of this research. As higher temperatures and climate conditions spread globally, the frequency and scale of wildfire damage are increasing worldwide. South Korea is also experiencing year-round wildfires and a growing trend toward large-scale incidents. Notably, this year saw unprecedented damage with five large-scale wildfires occurring simultaneously. This image presents the analysis of wildfire damage in Gyeongbuk, Republic of Korea, during April 2025, based on satellite observations from FIRMS. The fires and hotspots imagery shows the extent of wildfire spread, while the VIIRS NOAA 21 corrected reflectance imagery visualizes the distribution of smoke. Despite this growing threat, however, the current wildfire forecasting system and existing spread prediction systems have proven insufficient for establishing effective firefighting strategies and response measures. This has created a need for an intelligent wildfire spread prediction and response platform that can quickly and accurately predict how fires will spread. So in this study, Korea University developed a spread prediction algorithm using domain knowledge-based AI technology. And Seoul National University developed an AI-based integrated decision support algorithm for optimizing the development of firefighting resources, determining the most effective positioning of equipment and personnel. Then Gaia 3D integrated these technologies to develop a comprehensive digital twin-based WebGIS wildfire spread prediction system. Now let me explain in detail how we conducted this research. First, we built a database with the three key factors for wildfire spread: weather, terrain, and fuel, along with historical fire data. For weather data, we use 48-hour forecasts and to model detailed wind patterns in mountainous areas, and we integrated it with Wind Ninja software developed by the USDA. For terrain, we extracted elevation, slope, and aspect data from the National Geographic Information Institute's 5-meter resolution DEM covering all of Korea. For fuel data, we collected 4 type maps and fuel ignition characteristics. For fire history, we gathered data from 50 past wildfire. Using this data, we built historical fire parameter records using Sentinel-2 satellite images from Google Earth Engine. To analyze these fire parameters, we developed a deep learning-based module that automatically collects fire images. This module creates composite images from multiple data before and after the fire to reduce quality variations from single data images, then extracts burn indices. Now we With all this data, we developed a domain knowledge-based artificial neural network to predict ROS. The thing is, wildfire spread isn't just about simple speed. It varies significantly based on vegetation type, fuel moisture, terrain slope and aspect, plus wind speed and direction. Essentially, the spread rate starts with a base speed, depending on fuel characteristics, then gets modified by terrain and weather conditions. Our neural network learned from actual fire parameter data collected from real-world fire sites, and we use reinforcement learning to make predictions match actual spread patterns as closely as possible. The model continuously adjusts ROS and weight values, so over time it gets better at predicting how real fires actually spread. During training, when the predicted spread differs from what actually happened, our loss function calculates the area and distance differences between the two boundaries, essentially measuring how far off the prediction was. The AI keeps running to reduce this loss value and eventually inverts into a model that closely approximates actual wildfire spread patterns. To evaluate our algorithm, we compared predictions from both the empirical-based model and our AI model against actual fire suppression maps. We measured performance using IOU, intersection over union, which shows how much the predicted and actual burned areas overlap. Looking at the images here, you can see our AI model on the right has a higher IOU than the existing model, meaning it's more similar to the actual situation on the left. Next, we analyzed how to effectively suppress these fires when they occur. In Korea, helicopters are our primary firefighting resource. They can reach any location nationwide within 35 minutes from the nearest airbase. Leveraging this capability, we develop strategies for optimal resource deployment. Through this approach, we implemented an algorithm that takes fire information as input, determines suppression difficulty, and generates the most appropriate resource deployment strategy. To integrate all these AI modules, we designed the CI/CD and software architecture. When we push code through GitHub, it deploys to our WAS and web servers. We use open source like Geospatial, OpenLayers, and Cesium. For the data server, we use PostGIS. Specifically, we use OpenLayers for 2D map visualization and Cesium for 3D. For the 3D visualization, we actually landed individual trees nationwide based on forest type maps. And you can learn more about this in another presentation called From Forest Type to Trees. We also optimized the spread prediction model's performance by analyzing the existing system. Our test shows significant performance improvements, as you can see here. In our system, you can select and run different spread prediction models, and weather data comes from our meteorological module. Here's a comparison of the existing model versus our AI model, running under identical conditions. As I mentioned earlier, we can see the AI model matches the actual fire situation much better. We are currently validating the AI model by expanding our dataset from 50 to 200 fire cases. For the resource deployment module, you can also visualize results on the map. It shows routes connecting fire locations, water sources, and aviation management centers. It's still under deployment, but we are planning to add features like time-based simulations and more. Finally, let me show you the system we developed through this research. It has three main features. First up is the ignition information feature. You can move to any location you want and create ignition points or areas, and you can edit this after creating them. One notable feature, when setting inactive points and selecting vertices, we applied a freehand drawing method using OpenLayers. Now you can select any ignition point and run spread predictions. You can choose between the existing model or our AI prediction model to set up scenario, and you can manually adjust weather conditions. Results show up on both 2D and 3D maps, and when you run the module, you can check the options you set, along with terrain, fuel, and meteorological information for that area. When you select an ignition point and run the resource deployment module, it determines the suppression difficulty level. You can also input values manually to run the module. Also, you can see all the results right on the map. And that's all from my presentation. Thank you for your attention.
Does anyone have any questions for our presenter, all the way in the corner first? I work with the local fire service in Canberra, and I've got to say, we need one of these. Instead, we have people using human intelligence, which is not reproducible.
First of all, thank you very, very much for that. That was a very excellent presentation. Do you deal with fire suppression? Can you also add that into the mix, and the humidity? We didn't talk about humidity being an effect of reducing the fire if you've got high humidity. Fire suppression, do you look at moving aircraft around to protect valuable areas, and does that affect the impact in your AI? I can happy to talk to you afterwards if that's a little bit.
Thank you.
We'll talk later.
Oh, yeah.
Okay.
Any other questions, please? Yes, just here in the front. Alex, where are you from?
Where am I from? I'm from New Zealand. I'm from here, actually, Auckland. I work in aerial surveying, so I have a lot of experience with the kind of 3D DMs and stuff that you've been using for that, which is quite interesting. I was interested in the intersection over union metrics that you had for the burned area versus the predicted burn area. It said on there that I saw that you had about twice as the AI's version was 0.4-ish over 0.2. Does that mean that it's still missing 60% of the actual burn area, or am I misunderstanding how that works?
Thank you for your question, but I need to take some time to think about
Oh, no
it.
worries. It's complicated.
I'll get back to you after this session.
No worries.
Sorry.
Thanks, Alex. There is a Gaia 3D booth just over here, right?
Yes, that's right.
So anyone can come by. You're going to be here every day, right?
Yes, that's right.
Yeah, so are there any other presentations by Gaia 3D or just this one?
Yeah.
Just this one?
No, my super booth in another session
There's another session as well. Is it on just now or a bit later?
later.
Later, okay. So please look out for the other Gaia 3D presentation. I've got to say I'm pretty impressed. Would you please join me in thanking our presenter? Thank you.